thanks. Okay, hello, afternoon everybody. So, we've launched into section 2, and today we're going to look very, very carefully at a diagram, because this diagram is the foundation of the rest of the course. Okay, so understanding this diagram is crucial. It's not a complicated diagram, it just needs to be looked at a couple of times to convince yourself what's going on. So, to recap, I'll shut up in a few minutes in case someone's got any questions. No one's really put their hand up and shouted out anything, but do feel free to. Okay? So, we were postulating how it would be that we could get a motion of some displacement of the electric field which looked like a radiative term. That's another way to say what we were saying before. And we said that uniformly moving charges do not radiate. So we postulated a situation where I had an initially stationary charge, which then after a short acceleration becomes uniformly moving, but at a velocity which is small. We understand that we can extend this argument to other situations. So after the acceleration has occurred, this electric field line here is now moving uniformly, okay, albeit with a small velocity, and its field line afterwards is parallel to the original field line, which, of course, when you view it far away, the observer initially sees the old electric field, but after a sufficient retarded time has elapsed, you will now see the new field, which has shifted over slightly, and the region over which the field has shifted must be equal to the speed of light times the duration of time over which the acceleration occurred. So we recognise this as being the radiation that's emitted. And the astute ones of you will realise that the length of that electric field does depend on the angle at which we're looking at. We'll get to that later. Now, we saw before that the electric field component of a stationary or uniformly moving charge falls as 1 over r squared. That cannot be radiated. That's your static Coulombic field. The radiator part ought to fall as 1 over r, so that when we combine it with the magnetic field component, because we know those two components are coupled together, when we combine those two components together, their total energy falls as 1 over r squared, and again, that will satisfy conservation of energy, so we'll then realise that we have something which is a radiative component. Okay? So our task now is to figure out a way of seeing that this transverse component, because you see this part here, this total electric field, obviously there can be no sources or sinks at those little boundaries, so this little kink, which is quasi-non-physical, but we've said we're going to be happy with that. That electric field there does not point radially outwards, and it does not point perpendicularly, but the radiator component must be this perpendicular component here. So our task is to show that that perpendicular component falls as 1 over r. So we're going to replace this diagram with a slightly simpler one, which again is all in the notes. Okay. And now we're going to introduce a few more variables. So ut is the velocity of a charge in this direction upwards. Okay. And the bit we're interested in is this perpendicular component u parallel t. Now, think of the ratio between the length of this component, this E parallel component, that's our Coulombic field, compared to E perpendicular, which is this transverse component, which is our radiator field. So at the moment, this is just two electric fields. And what you see is as this radiative wave at this boundary moves outwards at the speed of light, this parallel component remains the same magnitude, whereas the perpendicular component grows linearly with time. Okay? So the ratio between E perpendicular and E parallel must be growing. How fast does it grow? It grows proportional to time, and because the radius, the distance at which that boundary is occurring, where the radiation is occurring, that is also moving proportional to r. So therefore, the ratio of this component and this component must grow proportional to r. Okay? This is what I call a heuristic argument. So we're going to say it in formulae, but that's what we're saying. So we're saying that the ratio between E perpendicular and E parallel grows proportional to time and therefore proportional to distance. So this argument, by the way, is due to a physicist called Edward Purcell. You should look him up. He did lots of really, really interesting things, lots of fun things with magnetic fields. Shows how you can shape magnetic fields with little holes in them. So think of a Purcell filter. So that's not for this course. Okay. So the reason he drew this diagram, he was trying to figure out a better way to explain why this radiative component has the form it does without having to invoke all the mathematical rigmarole of the retarded potentials and mathematical treatment. You can go to the other course where you can look at their notes and you can see how it's done that way. This way I think is a lot clearer because it encapsulates all the features of what we're trying to talk about. So you see that the ratio of the perpendicular to parallel components grows as a function of distance. So all we need to do is relate those two components together. Well, the other thing we notice is that the E parallel component, as you look, as R increases, the absolute magnitude of E parallel falls as 1 over R squared. Right? So therefore E perpendicular, E parallel varies as 1 over R squared. E perpendicular over E parallel, that varies as R, so therefore E perpendicular varies as 1 over R, which is what we're looking for. So it satisfies the condition to be a radiative component. Right? We'll talk a little bit more about what the radiative components, what that really means. So let's move that up a little bit. So let's write that down. So if we just do like a similar triangles argument, we can say that E perpendicular, just looking at this diagram, E perpendicular over E parallel must be equal to the component of the velocity, which is perpendicular to the observation direction. Remember, we're observing at some angle, which you haven't yet specified. It's going to be theta, isn't it? Divided by C delta T, which is the duration of that radiative transition, or that radiative boundary. I'm not using a particularly good word for that, but that's what it is. Okay. Now, of course, we can also write U perpendicular as equal to A perpendicular delta T. Okay? So what was A? A was thus the acceleration, which we assumed was occurring for a certain amount of time. So far, we've assumed a particular finite duration over which there is an acceleration which is uniform. Right? Of course, we're going to drop the delta T in a minute, and we'll see that this will also be true if any, we'll let delta T goes to 0, and this will be true for any acceleration. That's where we're going. Right? And again, this component here is the component of whatever the acceleration was, the component of A, which is perpendicular to R, the observation direction. Right? So then you can see ahead where we're going to be able to apply that A in many different contexts. So we can simply write down what E perpendicular is. It's equal to whatever the parallel component is, which we know falls as 1 over R squared, times A perpendicular T over C. Okay? The delta T's have disappeared. And it's therefore equal to E parallel AR over C squared, because we know that R equals CT. We know that the boundary is moving at the speed of light. Right? So all we have to do is do that careful observation of the picture. Okay? And we remember that E parallel is equal to, well, that's just the Coulombic field. Okay? The strength of the field, we know it falls as 1 over R squared, exactly the same as if the charge was stationary. It looks like a bit of a cheat the first time you see it, but it's straightforward, really. So therefore, we can directly obtain what the perpendicular electric field is. It's simply proportional to the perpendicular acceleration. Okay? Now, what we've done here is we've ignored the elapse of time. We need to plug back in when the acceleration occurred, okay, and appropriate retarded time, and compare it to when you observe the perpendicular electric field. I just haven't pulled that into the formula yet. The important thing we're seeing is the magnitude of the electric field, which is proportional to the magnitude of that acceleration. And remember that this is the apparent acceleration as viewed from a certain angle, right? The most important thing is we're seeing this. It's proportional to 1 over R. Okay? But like I said, we need to say that for any accelerating charge, the E perpendicular depends on A perpendicular at the earlier, i.e. retarded time, which remember we wrote down is tau equals t minus r over c. You can see it written in lots of different formulations, but I will use t for the actual acceleration time and tau for the retarded time when you observe it somewhere else. Okay? And this is exactly what we want to see. Now, we know that these wavefronts are not plane wavefronts when you're close to the charge. So there's some interesting stuff going on, right? Because you see, when you look close in to an accelerating charge, right, when you look close in, these waves have not properly formed yet. So there must be some near field stuff going on. And in fact, there's also a dipolar term. If you imagine an oscillating charge going up and down compared to some background charge, there will be a dipolar component that you've covered, which falls as 1 over r cubed. But far away, there's now this radiative component due to the acceleration, which falls as 1 over r. So there's 3 components. Okay? So the far field component, after we formed the radiation, is when we formed plane wavefronts sufficiently far away. And once we've done that, we know from our previous discussion that the magnetic field must have some form as follows. There must be a magnetic field that falls proportional to E. Okay? So the magnitude goes 1 over c times electric field, as we've seen. Okay? So the perpendicular magnetic field must be, in these plane waves, basically E perpendicular over c once we are sufficiently far away. Okay? And remembering, of course, B in our plane waves is perpendicular to E. Right? So this is for our plane wave. Now, that's the argument by saying when we're sufficiently far away we have a plane wave. You can also do this whole derivation by working out the magnetic field which is induced by a small generation of a current. Okay, so we looked at the electric field component and we said, how does the electric field change when I have a small acceleration? You can do an equivalent derivation and you can directly obtain the magnetic field. Okay, so you can follow the analogous argument for B by thinking about the current, and therefore you must be using Faraday's law to do this. So you imagine the charge starts moving and it generates a small current, but then when the current is changing during the acceleration period, you can obtain a solution. Okay, you can use Lorraine, Corson, and Lorraine to do that. Okay. But with this simple description, we have expressed a great deal, because we have clearly showed that in the case of an acceleration, let's say the acceleration is up, according to what's on the screen here, the acceleration is up, and we have a radiative component which goes outwards, and it's away from the charge in all directions, and it has a strength encoded by the pointing vector, okay, which tells us the energy flux, and the energy falls as 1 over r squared, as it should do, so energy is conserved. Very important statement. Now, what other observation can we make about the way the energy is flowing away from the accelerated charge? What have you spotted? Think about the magnitude of that perpendicular electric field at the top there, compared as a function of the observation direction. What do you see from that? You're all waiting for me to put it down, aren't you? Okay. Well, here is my accelerating charge. It's going up. So this is interesting. So the charge accelerates up, and the electric field change is pointing down. Okay? So the charge moves up and the electric field points down, so I have a down pointing electric field, and that is propagating away this way, and this way, and this way. What does the change of electric field look like when I'm looking down on the acceleration? So turn it round, the charge is accelerating towards me. How much radiation do I see from a charge which is accelerating towards me? Go on, just shout out something. Well, what is the component of the electric field when looking down on the charge? It's 0. Okay. So here is the same diagram drawn a different way. Okay. So we observe. So this is the acceleration of the charge. One more time. I put in that angle theta now, so we can write it down explicitly how it varies with theta. I observe at some angle and at some distance r, and you see that the electric field is pointing downwards. So when I view from this side, I have a maximum electric field, and therefore a maximum magnetic field as well. When I look down here and looking along the direction of acceleration, right, I see E perpendicular equals 0. Okay? So the electric field would be pointing sort of this way if it's slightly to that side, but the other way to slightly the other side. There must be a 0 there, right? So this must be the minimum electric and magnetic field. There is no radiation along the direction of acceleration. You only see radiation transverse to the acceleration. So that must be a very important statement. Okay? So, as well as the total amount of energy and the fact that it varies as 1 over r, we must also think of the radiation pattern. And again, some of you may be thinking, this is how radio 4 works. Okay? You look at that big, well, not today because you can't see anything out in the distance, but there's a big transmitter far away. There are electrons moving up and down on Winter Hill, and they're moving up and down. And this is why they're moving up and down. It's why they're not moving forwards and back. Right? They're moving up and down because that transmitter is roughly the same height that we are, and all the electric fields are maximum transversely to it, so it's not sending a signal up into space particularly. It is going that way, but not straight up. Okay? And the radiation pattern from that varies as a function of theta. Okay? So the radiation pattern from any simple acceleration or a combination of accelerations, such as going up and down, right, has the same basic form. Okay? So we can see here that the acceleration term, A perpendicular, well, that's simply whatever the acceleration magnitude was times sine of that angle of observation. Okay? So we can explicitly write down what the electric field is. I'm going to write it down as a magnitude. And I'm going to say, I'm going to put in properly the time. Okay? And put another boundary now. Okay? It's proportional to the charge that's being accelerated. You should look at that fact quite carefully. That will come back to bite us later. Okay? If I have a charge accelerating, the electric field from that that I get is proportional to the charge. Right? You've seen that that's concretely put in so far, right? There must be proportional to the magnitude of the acceleration at the earlier retarded time. Okay, remembering that tau equals t minus r over c. It must be proportional to the sine of the observation angle, and it's 4 pi epsilon naught c squared r, a factor. Okay? And that factor r, it's important to recognize it's different to r squared. Okay? So the pointing flux, right? This is a bit neater on the written up notes, right? I'm sure you're doing it neater where you're writing it down. Just happen to have this drawing done. So the power flux, okay, is simply relatable to the electric field. You can see both of them, yeah. Well, it goes as q squared, doesn't it? Because I'm multiplying the magnetic field by the electric field. Okay. So all those terms are exactly the same, right? I've just square everything. So I've got 16 pi squared epsilon naught c cubed r squared, right? The only thing that's appeared that's extra, the only thing that's appeared that's extra is that should be c to the 4th, but because the magnetic field is c times less than the electric field, it's only c cubed. Okay? Right. Where's that c? Let me just check that. A couple of typos in my own notes. No, that's correct. That's correct. The right way around. Okay? So the pointing flux, well, that's going to be given in watts per square meter. Okay. And what do we see in this? We see, again, it falls as 1 over r squared as it should for conservation of energy. I've put in the retarded time now, tau. The total amount of energy emitted is proportional to the acceleration squared. So double the acceleration, I get 4 times the energy emitted. Different to the electric field, it looks somewhat similar, but different to the electric field, there's an even stronger dependence of the power emission compared to the observation angle, as opposed to the electric field compared to the observation angle. So you should recognize that bit as well. So if we draw that out, shall I put that down here? Move that up there, there we go. So we can fit it all in. Pull that under there so you can still see the full thing. Okay, there we go. Just cover that bit up there. So that is a visualization of the pointing vector. Okay, so what this is showing, this is a radial plot. So here we are observing, now I've changed the thetas here, okay? No, sorry, that is the correct theta. Theta equals pi by 2, so when I observe, so the acceleration is up and down. When I observe from the side, I see this magnitude, this distance to here, and as I change the angle of observation, right, for each angle of observation, I have this much, this distance is the amount of power emitted. Okay? So the shape of that curve is sine squared, and you can see there is no power emitted upwards and downwards. But it doesn't matter which way around I'm looking from the side, right? This is a ring donut of emission. Okay? Possibly the greatest of all desserts. Okay. So we have a directional character to the radiation. Now the other thing to figure out, of course, is we've seen that the amount of energy that's emitted is proportional to the charge squared. Again, look very closely at that thing. That's a very interesting fact that will come back to bite us. And it's also proportional to the acceleration squared. But how much do we get? Well, let's calculate the total flux, or the total radiated power. And this is the most important formula of the course. I'm going to use it again and again. Okay. So the total radiated power and again, we started with a simple picture that Edward Purcell drew. What we have to do is think about the total amount of power being emitted into some overall sphere of radiation. So the first thing we do is let's draw a sphere. And I'm going to have theta equals 0 pointing up, so it must be theta equals pi pointing down. And at each observation angle, okay, over any small surface area, I have S emitted per unit area. It's watts per square meter. Okay? So I have to integrate appropriately over this sphere. So that must mean in any particular stripe, in any particular latitude, you might say, I must have an equal amount of power being emitted. So it only varies with theta, it doesn't vary with phi, the other angle. So there's theta there. And R is uninteresting, isn't it? But obviously this area element that I'm going to be integrating over, dA, that's over there, it's just the same old area element you're used to. It clearly varies with sine theta and d theta. So to get the total amount of power, and stick in the time, because I'm going to say that the acceleration might be varying with time. The total amount of power as a function of time is simply the integral of whatever S is at any particular direction, which is both phi and theta, but I integrate over 0 and pi, okay, because I can do that simple 2 pi when I integrate over phi. Okay? So let's do that explicitly. So that's equal to the integral of 0 and pi. So let's write it in carefully. Q squared is my prefactor, 16 pi squared epsilon naught. Okay? Then you've got acceleration squared. There's our retarded time. Sorry, let's call it tau. Consistency tau is our c cubed 1 over r squared. Okay? And then sine squared theta, right? That bit there, that's S, isn't it? Okay, just broken apart the sine squared theta and put it on the right. And then the dA part, I'm going to run out of space on the side here, but it's 2 pi r squared sine theta d theta, that's dA. Okay, all right. So that means the total amount of power emitted, okay, P is a function of T. You have the magnitude, right? So I do all the different factors, I take that factor 2 across, and I get 8 pi epsilon naught c cubed, proportional to the acceleration squared as before, that should be tau. Okay. And then I simply have to integrate those angle parts. So I've got the scaling of the area, which goes to sine theta, and I've got the sine squared theta, which is the power variation as a function of observation angle. So that's sine cubed theta d theta. And that turns out to be 4/3. That's interesting because you don't often expect to see these factors of 3 appearing in these calculations. So that's where that sine squared term is contributed to that, which is why there's a factor of 6 in the final answer. Q squared over 6 pi epsilon naught c cubed a squared of tau. Okay? So that's the total amount of power emitted as a function of time. So clearly if the acceleration is a constant, the power is a constant. And again, we see that basic feature that the total power emitted is proportional to the acceleration squared, and it's proportional to the charge squared. And again, look at that charge squared thing. Imagine 1 electron, and imagine 2 electrons near to each other. We have to worry about that later. For now, we'll just think of it as a simple charge, and we'll think of it as a lump of charge as being somehow a point-like object, but we do have to worry about that later. So this is Larmore's formula. So this is basically the entire course. Okay, we're going to look at the consequences of Larmore's formula, and we're also going to look at the relativistic generalization. We're going to start looking at what happens when we have very rapidly moving charges, when relativity comes into play. Okay? And we used Edward Purcell's method to obtain it, okay? And we like that because it lets us very conveniently see all the physics rather than worrying about the mathematics obscuring it. Okay? Which is why I'm showing it here. You can go through the same derivation in other ways to make it less obvious, I would suggest. Okay. Right. So just to recap, any questions? Is that clear enough, hopefully? Well, wondering where this is all going to go, right? I'm going to put the notes up a bit later if you're not sure where it's all going to go, so I know I've not put them up yet. You've got to have some reveals, haven't you, in this kind of course. Right. So this was for, remember we started with a small duration acceleration of delta t. We showed that we could let that acceleration drop to 0 duration. And this is the instantaneous acceleration giving an instantaneous power. But I did imply that there is an interesting situation where I have an oscillatory motion of a charge. Obviously oscillatory motions of charges arise very, very frequently. Imagine electrons in atoms, or electrons in a conductor in an aerial. So the first thing I'm going to look at is the simplest demonstration of the physics of that, which is called the Hertzian dipole. Okay. So we'll move on to that. The next section is radiation not from an instantaneously moving charge, but from an oscillating electric charge. But I'm going to say an electric dipole because we're going to think about a charge moving with respect to another oppositely charged object. So we're going to use our basic Larmor formula and consider an oscillating current element. Oscillating current element. So clearly you know that a moving charge constitutes a current, so we can think of a moving charge as being also equivalent to a current. So we can think of either generating the electric field pattern or the magnetic field pattern, but we realise that they're equivalent pictures. Okay? So let's look at the oscillating current picture. this will illustrate the magnetic field analog of what we just did for the electric field. So imagine two locations. I'm going to label them 1 and 2. And I imagine a current flowing between them, which is varying. So clearly the charge is rising and falling on each point 1 and 2. So there must be an oscillating dipole. Okay? So I can write down the charge at point 1 is equal to some total amount of charge, say e to the minus I omega t, where omega is the frequency with which the charge is moving backwards and forwards. And I can write a similar picture for the amount of charge at point 2, and I assume the whole thing is in total neutral, so it must have the opposite value. So if I think about the current flowing in between those 2 points, that must be I equals dq1 by dt in the z direction, because I'm going to have to start thinking about what that means in terms of the electric and magnetic fields. So if I write that down explicitly, it's minus I omega q0 e to the minus I omega t in the z direction. Okay? So just notice we're doing z here rather than x because we're thinking of up and down. Right. Now I've just put in those 2 points 1 and 2 with some arbitrary separation. Let's imagine we have a very, very small dipole viewed far away, so I just have a small amount of current flowing between those 2 points. I imagine a separation going to 0. So all I basically am seeing is a current whose magnitude, okay, current magnitude goes as I omega q0, okay, magnitude of current. So this is our different picture compared to the electric field picture. So of course, we can work out the magnetic vector potential. Yes. And this is, let's do it explicitly just once to show how it can be done. So the magnetic vector potential is on the left this time. So remember our magnetic vector potential has some prefactor. Okay. And we take, so we write it down in our original form first, to remind ourselves. We have a current density, right, which is present at some location r primed at some time t primed. I just add up over all the volumes where it's present. And the magnetic vector potential is proportional to the distance, inverse proportional to the distance of observation, to whatever's going on in those moving currents. But in our particular situation here, we can write it down explicitly. Same prefactor, but that integral reduces to something like I naught L. This is, when I do this integral, I have a certain amount of current over a certain distance. So this integral here starts to look like I naught L, where I naught is the amount of current and L is the distance over which it's acted, but in such a way that as L tends to 0, okay, I naught L must stay the same. Okay, so that's how we're going to understand that term. Okay. But clearly it's not a constant current. It must have, I'm going to put the right hand bit, it varies as a function of time. So there's an I omega t there. Okay. And when viewed at a certain distance, I'm going to ignore, well, I'm simply going to say when viewed at some distance r now, okay, because it's independent of, when we think about the distance to our observation, it doesn't depend on phi, okay, and I can say simply proportional to r, 1 over r, where I'm taking my current element to be at r prime equals 0. Okay. It's a slightly fiddly step. Hopefully you can see how that works. So once I've got that vector potential, I can directly obtain the field. It's just the curl of that. Right? So when I take the curl of that, this is being done in spherical polar coordinates. So we're going to stick in a prefactor here. Okay, make these nice big boxes, we've got the space of everything in. r hat, you may not have seen this for a while, but look back at your notes. R sine theta. Phi hat, it's a bit more paper. It's scratchy. There we go. And d by dr, as usual, d by d theta, d by d phi. And then I've got the spherical polar coordinates, AR, RA theta, okay, R sine theta, A phi. Okay. So my job is to relate this A to those three components. Well, let's think about that. I've got a dipole. I've got a current going up and down. Okay? And we already know that when a current is going up and down, that the magnetic field as it's going up and down. Remember, when the charge goes up, or the current is in the upwards direction, the electric field is pointing down, and the magnetic field is transverse to that and transverse to the propagation direction outwards. So it must be around. Okay? So it's just like any other current, the magnetic field points around. So in the radiated field, we already know that there is no outward component, and there is no theta component, there is only a phi component. Okay? You can prove that by following that derivation through explicitly, but we can already see by observation that Br and B theta are both 0. That's exactly as we would expect. There's only a phi component for the magnetic field. Okay? So if you follow through, it takes a little time to substitute that all in, you will see that B phi, well, we must have that mu naught over 4 pi, that must be appearing there. Okay? We have the magnitude of the amount of current over the distances moving, and we'll put that in brackets to remind you. That stays a constant, we let L tend to 0. We've got K sine theta, okay, where K, go back here, that K was encoding the phase change between the point at which the current is moving compared to when I'm observing it. Okay, so what that means is this is C equals over K. Okay, and where have we got with that? Yeah. Okay, so theta, and if we work out these terms, and I'm not going to ask you to remember how to do this derivation, by the way. I'm just showing you that it does work out like this. Okay? There's actually two phi terms that appear from the two parts of the cross product. Okay? And one has an I in it, and the other one doesn't. One has a 1 over r in it, and the other one doesn't. And then there's an e to the I, kr minus omega t over r. Okay? Right. So what have we shown? We've tried to show the steps to calculate the magnetic field arising from a moving current. This is as a contrast to what we did for the electric field. But I'm trying to show you here that from observation we can see that if there is a current moving upwards, there is no r and theta component, and when we work through this cross product, we see that there are two components that arise, and you can hopefully see that one of them goes as 1 over r, and one of them doesn't, it goes as 1 over r squared. Okay? So presumably this one here, that's the radiated component. Now, just to finish off, we can, of course, calculate explicitly from that. We can take the curl of the magnetic field, and this is in free space, away from the moving current. We can relate the magnetic field and the electric field together, and one is just the curl of the other. Okay? Remember, this is in spherical polar coordinates. Okay? So we've done that, so we know there's only a phi component of the magnetic field. Of course, in spherical polar coordinates, there will be two components of the electric field when I take the curl, and now the phi component is equal to 0 because the magnetic field is perpendicular to the electric field. Okay? So these are complicated expressions. Right? To save writing them out, I'm just going to pop them up here, so I don't ask you to write these down. Okay? So here it's all in one go. So again, I'm not asking you to remember this, how to do this derivation. This is to illustrate how we can go directly from the current through the vector potential to work out the magnetic field, and we apply an observation that says that it's only the phi component of the magnetic field that exists, we take another curl to get the electric field, and we get a set of components that appear. Okay? So what we're going to do is we're going to look at those. Right? But we note this is a complicated expression. Right? This is why we don't try and do it directly. We do it via the vector potential, where we can at least simplify things a bit. So we see in the electric field, we see a 1 over r squared term. That is the Coulomb field. And the only difference is a phase term. So it says as the electric field rises and falls, so does the electric field at some distant location, but I have to retard. That's where the retardation is coming from. This bit here is 1 over r cubed. So that's not radiative. So that's not the radiative term. The radiative term is E theta. Okay? And that E theta goes with B phi. So there's your 1 over r term there. Okay, this plus this here. That's the radiative part of the magnetic field. So we just have to see that this one here, oh, there's a radiative part there. That's the 1 over r. Okay? And notice there is a phase shift. Right? When the electric field is doing one thing, for the Coulomb field is doing the other thing for the radiative field. There's this other bit here, this is your 1 over r squared, that's the Coulomb part of the electric field. This bit here, this bit's the Coulomb field because it's 1 over r squared. This bit here is the dipole field because it's 1 over r cubed. So there's several components that appear. Okay? So this derivation is meant to show that you can see all these things appearing, and they all have different variations of r. So you can see that close in, you see predominantly the Coulomb field. So when you're very close to the charge, you see only the immediate field as a function of distance. That drops as 1 over r squared, right? You also see this dipole component that falls as 1 over r cubed. When you're very far away, you only see the 1 over r component. That's the far field radiation term. Okay, so those are your three terms. Okay. That's what we're saying here. These are your regimes. Okay. So you have a near field regime, and we can code that by saying it's when Kr is much, much less than 1. So remember, K is proportional to the wavelength. Sorry, 1 over the wavelength. Okay. What we mean by that is the distance from the dipole is much less than the wavelength being emitted. That's what Kr much less than 1 means. So in this situation, we have three components. We have the dipole component here that falls as 1 over r cubed. Okay? That's our near field regime. Whereas in the far field regime, so this is basically showing the other way of doing that derivation. So the far field regime is when the distance is much bigger than the wavelength of emission. And then you have two remaining field components. These are the components that have formed as 1 over r, not as 1 over r squared or 1 over r cubed. And they have the right kind of form. So let's look closely at them. Right? Firstly, they have the right relative strengths. Yeah? See those two bits there? They differ by 1 over c. They're both proportional to the amount of current that's moving, i.e. the amount of charge that's moving. That's those bits. So obviously when I multiply these two terms together, they're proportional to the current squared or the charge squared. Okay. Then you have this bit here which is telling you about the time variation. The omega t is just telling you that the charge is moving up and down with a certain frequency. And this bit here, this Kr, that's encoding your retarded time. That's how many wavelengths you are away. And then you see these two components. Remember we said that if a charge or a current is moving upwards, right, then the only component of the magnetic field in the far field is the phi term, is the one that's pointing around the motion of the current. And the only remaining term in the electric field far away is the theta term, which as we see is perpendicular to it and pointing that way. Okay? Current goes up, field points down. So as we saw before, when we look along the direction of observation r, okay, that's the direction of motion of that electromagnetic wave, the magnetic field is still perpendicular to the electric field, and if you look closely at these two components, you'll see that they differ by a factor of c in magnitude. So the magnitude of electric field and the magnitude of the magnetic field is still c. But there's another important thing. everything still rises up and down in phase. Okay? So the magnetic field and the electric field rise and fall. Okay? So remember what we said about when we did it for the plane wave solution. We said that in a plane wave, the electric and magnetic fields rise and fall in phase with each other. Okay, in a plane wave. And here we see explicitly when we have an oscillating current in this solution that we can obtain, which I've sketched out for you. I've not gone through every step, of course, right? I've sketched it out for you. I see explicitly those components appearing. These are the far field components. And they also rise and fall together. You can see they rise and fall together because of these two terms here are the same. Okay? And also, those two terms there, this minus I is essentially a phase difference. It's a phase shift, isn't it? There's two minus i's there, so they have the same phase. Okay? But again, the electric field still varies as 1 over r, as it should do for radiation. The magnetic field varies as 1 over r, as it should do for radiation. And the total amount of power can be written down in terms of, so rather than now in terms of the charges moving, we can write it down in terms of the current, but we see the same basic behavior. We see this prefacted 6 pi epsilon naught c cubed. Okay. We see that the power emitted is proportional to the current squared. Same thing as the charge squared, isn't it? In this particular case, we've assumed an oscillating current, so we have a frequency that appears, and this is where the retarded time is appearing. It's appearing here. Okay. And the other thing we see is this is the length of the dipole and the frequency that really can be combined with our I0 term. Okay, as we'll see in a minute. Okay. That's a lot to take in. I think you should read through that section of the notes again, but keep hold of that basic fact about an instantaneous acceleration being observed far away. And the key things to remember, I know there's a lot to take in this lecture, right? It's a Horace one folder. The key things to remember are that we've gone through to say how an acceleration gives rise to an electric field. Right? That's one way we did it, and we realised that in a plane wave, the electric and magnetic fields must be coupled. Here we've done it the other way around. We have directly calculated the magnetic field from a moving current, and we've described its geometrical properties, and we've explicitly gone from that magnetic field to the electric field. But when we did that, we saw those extra components, right? So as well as this far field component that falls as 1 over r, we've directly seen the other components. The Coulomb component, which goes as 1 over r squared, that's for the electric field, and the dipole component, which goes as 1 over r cubed. We've sketched how that works. Okay? So, what we'll do from now is we'll go on and look at the consequences of that in a number of different contexts. Okay? And we'll do that on today's Friday. We'll do it Monday. you, mate? You're right. Yeah, have you seen The Office? Have you seen The Office about your essay? You're just going to let it go? No, I haven't. Yeah. Okay, you're going to let it go? Yeah, I think I will. At the end of the day, most of it is just going to... I've still got the marketing papers to do. Yeah. So 70% is actually on the essay anyway, so... Yeah, so I'm sorry you couldn't make it, but we have to set a time for it. Oh, yeah, I get that. Did you follow that on okay? I know, this is probably the hardest of the lectures, I would say. I quite enjoy this sort of stuff anyway, so... Okay, good, yeah. I do a lot of photonics-based things, so finding all the waves and things like that. You need to get some feedback, you see. Yeah. Do you want it back over? So I need to go in there.